Mexico City and the Monterrey.
Monterrey.
Yeah, we had a healthcare innovation conference at the one of the campuses of the Tec de Monterrey. One of the most prestigious universities in Mexico.
Yes. That's where, isn't that where Hector Garcia went?
Yeah. It was actually, Hector Garcia Molina's father was the president of that university, second president of university
Okay.
for 24 years.
Yeah.
Yeah, that's I could see a very smart student there too.
Yep. Yeah, we've been
Okay,
hiring.
go ahead.
So yes, we hire a lot from Tec de Monterrey. It's a very good school.
Yeah, right.
Yeah.
So yeah, I'm actually pushing some collaboration with that university. That university is also interested in our experience.
Yeah.
Of starting big data institute and then starting the graduate school of data science. Yeah. Anyway, let's get started. Today we have a very distinguished speaker, Tatanka Lahiri. He's my old friend, and once he was also my enemy. So
Professional competitor.
right. He can talk more about that. He has a long time experience of developing in-memory database, and also, he's been, I think I don't know how many years he was there, but he was with Oracle a long time, and he's currently SVP and plays a key role in at Oracle in the database technology development, etc. Today he's going to talk about the relational database and also object database, and then object relational, and then document. Converging three of these. Thank you. It's yours.
Okay, thank you so much. Thank you so much for that nice introduction. I'm very honored to be acknowledged by someone of your stature. So honestly, this is you've made my day by the things you said today. So thank you so much. So yeah, I've been at Oracle now I was actually in the Stanford PhD program for various personal reasons. I had to take a little time off to work for a year. I thought I'd work for a year or two and come back and finish my PhD. That break from PhD became longer than expected, and I've been at Oracle now for about 30 years. But I did spend a lot of time at Stanford, and I did work actually on my PhD, which I didn't finish, but I worked on multiple areas, including operating systems and semi-structured data and lots of things that eventually actually became JSON. Interesting. Actually, my last research in Stanford was about how to make semi-structured data representations for databases actually work properly. And it turned out the stuff we were doing then became JSON today. So this talk is basically full circle for me. So let me share the screen here and go back to where I am. So this is the keynote presentation I presented with my current manager, Juan, and in ICDE. I'm just going to go through this again with you because I don't think anybody here attended ICDE. Is that correct? Has anyone attended?
No.
Okay.
Almost not. Yeah.
All right, great. So let me quick. So this I think will be an interesting topic for an academic audience because it is slightly higher level than a traditional industrial talk. So let me see what you guys all think about this. So the idea is that databases need data intention to make databases great for development and also for AI. And what does that mean? So databases, honestly, databases were, when I joined the field, most business applications were written using the logic the database provided. But now what's happened over the years is many applications tend to use databases only to keep data persistent, and the logic is all done in the application tier. And the reason is actually very simple. It's because I think a giant miss on the database community is that we never really looked at the really difficult problems that developers face. So as a result, developers decided to build their own solutions and use the database as a backing store while they solve the problems inside the application. And one reason databases have not done a good job in solving developer problems. By the way, please tell me to slow down or speed up as you see fit. So if you think I'm talking too fast, or if you'd like clarification, let me know. But I'll try to keep a pace that will let me get through at least half the presentation. There's a lot of slides here I can't cover. I'll try to cover the major concepts. So basically, to get back, the solving really difficult application problems requires database to understand what the application's intention is or intent is. And today, databases have basically two languages. Any database, no matter which database you look at, have a data definition language, which tells you how to organize and create data, and a data manipulation language, which specifies how data is accessed. That's basically what every database, including Oracle, provide today. What is missing is a language to declare data intention, how data is supposed to be used. And this we call the data intent language, which is DIL, not DDL or DML. And why do we need this? One big reason we need this is one of the most basic problems for relational databases. It's called the object relational mismatch. This has been a day one problem with the relational database. And the problem is explained as follows. Imagine you have an application object, and every application is written using object-oriented programming. So a purchase order will have a number of items inside it, for instance. That's the way applications think of data. But when you look at the database, it knows nothing about that object. It just sees the data in relational tables. And we are oblivious of the fact in the database that, in fact, the application doesn't want to think about tables. They want to think of things as objects. This is what's called the mismatch. And this is a messy problem for developers to solve. And I've been in the field for many years now. When I was doing research in Stanford, there was a whole generation of what were called object databases, which store data natively in objects. Then came about object relational databases, which were hybrids of relational databases with object support, which added fairly complex types and various rules to databases. Now today, there's a lot of frameworks that are called object relational mapping tools, or ORMs, that basically hide the database behind layers of code to map language objects to tables. And of course, now we have a lot of document databases like MongoDB that store data natively as JSON instead of as tables. So that's kind of the attempts that have been made in the past. None of these are very successful. Object databases died because developers said, I don't want to deal with two different type systems, one in the database, one in the application. Object relational is around still, but it's not widely used because it does compromise some of the basic benefits of the relational database model. None of these solutions really work. They don't really solve the problem. And I'm going to give you an example of this problem through through a real world, a simple scenario. Imagine we are trying to build an app that is tracking the schedules for students in different majors. So each student takes a list of different classes. If you do the right thing from the data standpoint and store the data in relational tables, it's the best way to store your data because you get modularity of data. The data is fully consistent. You don't duplicate your information. You can compose this in many ways to create the data you want, and you get declarative queries. So it's a very powerful way to represent your data as independent tables. Now, the problem again you get into as a developer is when you read this data, what you're getting back is a set of rows that you can compose basically by joining the different tables. You're not getting an object back, you're getting rows back. But rows are not great for developers because for many reasons. First of all, they're rows, they're not objects. And secondly, when you read a set of rows for a particular student or for a particular use case, you're going to get back a lot of duplicated data. Like in the case of a single student, Jill, when I read her course list, I'm going to get duplicate results because every row will have the same information repeated for all the levels in the hierarchy above the leaf. So applications don't like this, and they can either deduplicate the data or they can read multiple tables independently and construct a hierarchical object. not fun for developers. It also becomes really messy when you do updates. So when the app developer wants to just update Jill's schedule or Jill's course list, you have to update multiple tables, which is much more tricky to make consistent than the reads even. So this is not fun for developers. This is why JSON databases have become very popular. In fact, one of my, like I said, one of my research projects was how to make it possible to do something like this by keeping the data in a structured format in the database. So in a way, this is back to full circle again. Almost 30 years later, I'm back doing the same thing at Oracle. But now there's a new framework for doing it, which is JSON. It did not exist when I was doing my research. At that time, everything was XML. So JSON is nice because if you look at the thing on the left, it looks exactly like the object you want on the right. So JSON has become a universal standard for representing, semi-structured data. You can easily, if you store the data in JSON, you can easily get the data as a self-contained JSON document, which the application can then edit and then write back to the database. So it's all very simple. With JSON, you don't lose any of the native properties of the object that you want to support. You can just do gets and puts. And this is why databases like MongoDB are very popular, because the database essentially becomes a mirror of the application data model. And to address this, every database, major database, relational database, including Oracle, have added the JSON as a data type. So you can actually do the same thing in this slide I just showed you with the Oracle database too. You can read it into a JSON column and write it back. That's all fine. So a single database can now support both relational and document data, providing the benefits of both. So now you can have relational data or document data in the same database. Now, the problem is if you store data in JSON directly, it creates the problem that the relational database actually tried to solve on day one, which is it creates data duplication. So if I store my data as JSON documents for all the different students, every student taking the same class will end up with duplicate values for that class in their documents. If you see in this example, math is a class that both Jill and Lucas take, and their documents contain that data redundantly. And this creates multiple problems. First of all, it makes the database bigger. It also makes updates tricky, because if I want to modify, say, the classroom for the math class, I have to go and update lots of documents, which becomes slow, and it creates the possibility of errors, right? So this is not a good way to store not the best way to store the data. It also gets worse when you use the same data to represent multiple use cases. Like, we began with the student schedule use case, but as you know, most apps will add more functionality. And let's say add a new use case that says, I want to also look at course requirements or curriculums. That app module on the bottom will share the same data with the app data on the top. And in this case, the curriculum document has a course as the root of the document, but shares all that course information with the student document. So every student has some of the information that's also present in the course document. So this problem is worse. Now, how do you solve this problem of duplication of data using JSON databases today? Okay, is there a solution for this? There is I would say a workaround in JSON databases today, which is document references. So what the MongoDB developers will say, you don't store the document inline, keep a reference to another document. So you have the student document, you can reference other documents. And basically the references allow you to effectively normalize the documents to eliminate duplication. And then queries can aggregate the content from multiple documents to create a single result document. So you can assemble the document you need by following references. So in this example, for instance, instead of storing the data the way you want on the left, you have a parent document, a root document, the student's schedule, that references a student document, that references a course document for each course. and that references a teacher document. So you can imagine how this would work. Now you don't have a single document, but you have multiple documents that you can compose into the document you want. Now, why is this not a good idea? Because the main reason for document databases was to simplify development, and this loses simplicity because now you're normalizing documents just like you normalize tables. You now basically have a document structure that looks just like your relational schema. So you've brought back that very problem of normalization across different data modules. But it's worse because a relational database can get away by doing this because, databases are very sophisticated query optimizers that can pick the right join orders and join methods and so on. You can't do that in document database. Document databases will always traverse references like pointers, and this causes bad performance, and you lose locality. I mean, one benefit of document databases is you can partition your database by document ID and access only the local documents given a certain ID. But if you have to follow pointers, then you lose the locality of reference. Updates to data becomes very cumbersome because now you have to go and chase all these pointers to update the document. So this is not ideal. So I've given you a problem statement. How can we solve this problem of providing hierarchical data that is meant for applications, that is self-contained and customizable, while keeping the power of the relational model? We don't want to lose the power. We want the simplicity of documents with the power of relational, right? That's the main problem we're trying to solve here. And this problem is again caused by the one simple fact today, that everything in databases today is storage centric. That today, when you specify the storage model, that dictates everything about the data, how it's used. It says the operations, language, and APIs are all storage centric, not use case centric. When there are multiple use cases for data, not everybody wants to think of data as rows. In this case, I'm telling you, people want to think about data as documents. In some cases, somebody might want to think of data as knowledge graphs. This is difficult today because the database says storage format dictates everything. The idea is, again, if the developer could declare how they intend to use the data instead of how they just intend to store the data, then you could have come up with something that matches what developers want to actually do with their data. And this lets the database generate, in the AI era, that's very important, generate the format and the APIs that are best suited for every use case. So that's the idea of data intention. And, there's a paper from Google called Attention is All We Need. We claim the other, the sort of the equivalent idea for data management is intention is all we need to achieve the original vision of COD's relational model of applications being independent of storage. COD, the Boyce COD was a visionary, I think I've forgotten when, many, many years ago, that envisioned a new type of database that would basically decouple access from storage. That was only partially made true because in his model, everything was a relational, sort of map that was stored in storage in a different way. But relational is not sufficient, as I said, because of the way applications want to use data. So we need more than just relational abstractions to get intention to drive data design. Now, today, there is such a thing as data intention partially. Today, a view can let you also compose data from multiple tables into a single result. So if I want to look at schedules, I can create a view that looks at my data as a schedule would. You can flatten this into one table structure that gives you the data you want. But views have limitations. They were always meant to remain relational. They're never meant to be a bridge between relational and some other model. And they always use row-level APIs. So ultimately, you're still stuck with rows. And views have lots of restrictions and updates. Like a view like this, you can update certain things, but not other things. You can update essentially the fact rows, but not the dimension rows. So what is the idea? The idea that we came up with in Oracle database recently was something called the JSON relational duality view concept. And here, this is a concept, it's a new kind of view that provides duality of data models. You can view your data as JSON without having to store your data as JSON. And this is called data model duality. It's a very simple thing to set up. So you have a bunch of tables from which you have your data, and you can declare the view using, we can use it, you can use SQL. We also support a language called GraphQL that is simpler for something like this than SQL to make it easy. But basically you specify the view in terms of the tables you want to access the data from and the columns. So, each of these fields references a separate table name in the schema. And each of the fields represents a column name in each table. So you can see it's very simple and intuitive because this view definition looks just like the data you want to generate, right? That's called data intention. I want to access my data in terms of a student object document, okay? Once you create the view, it's very easy to query. You can treat it just like a JSON document. You do not have to do anything special. It's a JSON document you can do gets and puts from, or you can use SQL, no problem. You can modify the document too. You can read the document into the database, into the application, modify it and do a put on the document into the view, and the database will automatically figure out which tables are affected by the write. So it's both read and write through document APIs. And the beautiful thing about duality is, even if I read different documents from the database, I might think that there is duplication of data across the different student schedules, but in reality, there is no duplication. This is only generated on read. There is no duplication because your underlying storage is in normalized rows. There's only one copy of course information in the database, and the student table and the Lucas table have references basically that let you know that, hey, they're taking these courses. So it's very simple that we don't duplicate data. The big benefit here is this is actually JSON done right for databases. It delivers a promise of simplicity that you do not get from a pure JSON database. You can also create any type of data shape you want from that central set of tables without duplicating any data. By the way, we have a paper accepted in SIGMOD later. I think it'll be in June. If anybody is attending SIGMOD, you should come to our talk. I think it's in Berlin in June. But we'll go through duality deep dive in SIGMOD. But again, just to get back to this, if you look at this example, I'm generating 3 different data use cases without having to create multiple copies of my data. That same underlying table structure, student course, the student course mapping table, and the teacher table can generate the student schedule, the teacher schedule, and the course curriculum without any data duplication. All of these documents share the same data, but there is no duplication in the database. And the application can still keep doing single object reads and writes and get full consistency. So it's not that JSON is inherently bad for data storage. In some cases, you want to keep some data in JSON format because there are many examples of data where you do not know the structure in advance. So if you have unknown data of unknown structure, or that's maybe flexible or changing, you can certainly keep a JSON column for that data. Like for instance, I might have like a prerequisites or requirements column in which the requirements, the format keeps changing. Maybe I have a list of courses to take. Maybe I need a minimum, passing grade. Maybe I have to have taken that course within a certain period of time. You can add all of that as a JSON column to the table, and that still is fine with duality. Duality can also expose JSON data as JSON. We also, because we're database people, as Professor Sang will tell you, that we think a lot about concurrency control and making databases transactionally consistent. So we did work on very hard in making the JSON relational duality model work well for transactions. Now, one thing about the modern world is I think every single one of you in the audience today have a smartphone. And the vast majority of database interactions today happen from some people using their smartphone for doing various things, whether it's banking or travel bookings or whatever it is. Because you're working from an end mobile device, you really want an API that is stateless. You can't have state on a mobile device because you might get disconnected. So that's why, stateless APIs are popular. That's why REST APIs are so popular, where you just do gets and puts across an HTTP connection. Now, this is very difficult for transactional applications because in a transactional application, you need to be able to hold locks across different database calls. And you can't do this in a stateless application. If I'm doing independent REST requests, I can't open a transaction and keep locks held until the transactions commit. It doesn't work for this environment. So how do we do concurrency control in this new world? This is done by using lock-free manipulation. You have to use a different technique where you essentially allow the operation to run without holding locks. Now, a lot of frameworks today allow lock-free concurrency control by adding version numbers to objects. For instance, if I add a version number to the student schedule object, every time I modify anything in the object, I can bump the version number. So when I get a new update, I can say, hey, is the version number still the same? And otherwise rejected. But this doesn't work for objects where the data is shared. Like if I have a course object and a student object that share the same data, I am not going to be bumping the course version number if I modify a student version object. So they don't really work. And this is, creates the possibility of deadlocks and is also very inefficient. So version numbers don't work. The idea we had was instead of version numbers, use the actual values, and we call it value-based concurrency control instead of locks or versions. And we came up with this idea. It's not really a new idea. It's already done in HTTP, but there is a concept called an E-tag in HTTP. When you read a document in HTTP or any resource, you get back a result that includes the E-tag or the hash of the result. You compute the hash on reads, and you verify that the hash hasn't changed when you do a write. And this avoids lost writes. If the hash has changed since you last read the document, we tell the application, retry the write. That avoids lost writes and gives you full transactional consistency. So that's the exact same idea in the database. You take that E-tag, you compute the hash of all the rows that contribute to the object. When you write the object back to the database, we make sure that the E-tag is still the same because the E-tag is actually part of the document. So the document, when you read a document from the database, you get the document along with the E-tag. When you write the document back, you get, when you write the document, the write is disallowed if the E-tag has changed. Make sense? So this is the best, this is the theoretically sound way to update data without holding locks and version numbers. There is nothing that needs to be maintained by the application. The application just gets the document back anyway. There's a field in the document that says what the E-tag value is. And on the right, the E-tag is consulted. And if the E-tag is changed, then the write is rejected. It's extremely simple conceptually. Okay. This is called value-based concurrency control because there is no secondary data structure that's tracking concurrency like locks or version numbers. It's by checking the actual values. So this is bulletproof because any change will change the value and guarantee that your E-tag will not match. And also this works across different object type shapes. So if a student wants to update their data and the course administrator is updating, or the course curriculum administrator is updating the curriculum requirements, they can do that consistently because there is only one actual copy of data in the database, but you can ensure by using E-tags that only one will succeed if shared data is modified. This is very difficult to get to work with locks or version. Even locks don't really work. If you have real locks, you would end up potentially getting deadlocks and have a lot of deadlock problems. And version numbers certainly don't work because the version number is object specific. It's not global. So this is not going to work. They also allow you to, this idea, by the way, works for any type of update. You don't have to also use duality views or JSON documents. You could basically synchronize across essentially regular relational updates and document updates. So it's a simple extension that allows you to synchronize across multiple types of workloads. Another thing just a subtle thing I'd like to mention, not every field is super critical when I do a put or when I do a write of a document. For instance, if I want to add a course to my schedule, and let's say the classroom from another course has changed, that shouldn't result in my write failing. So because I'm not actually modifying the course details, I'm modifying the course list. So I can say, hey, if the course classroom has changed, don't bother to, change the E tag. So you can say that the classroom is no check. So if it changes, it doesn't prevent the write from happening. And this is a bit like column level locking or element level locking, which is also a very powerful feature. It gives you very fine-grained locking and lets you ignore changes that are not important for the application. So this way, if I wanted to add a math course, but my science course's classroom has changed, I'll tell the eTag, compute engine that it doesn't matter. Allow the write to go through. Okay. So there's many, positives in value-based concurrency control. This lets you maintain full consistency for interactive mobile applications without locking data. Gives you fully consistent caches. When a cache is updated, when it writes back to the database, the write can be rejected based on the E tag. And if the database crashes and I fail over to another database, I still preserve consistency. So that's another very powerful feature that, it doesn't matter where the database restarts, I still maintain full transactional consistency and have consistency across replicated database. Even so I have a replica, I can check to say, hey, is my E tag there up to date or not? So it's a very powerful feature that works for many different, very tricky problems. So basically, relational databases, and I've been in the industry for many, many years. It kind of pioneered the idea of navigating data using values instead of actual pointers. For those of you who are old enough to know or have studied database history, before the relational database existed, there was a data model called, I think, the network model. It was actually even before my time. It tells you how old that was. In the network model, there were actual physical pointers to data stored in the database. And the relational database came back saying, no, you don't want to do that. You want to store a reference based on a value. This is another evolution of that concept to allow it to be used for concurrency control, where the values replace the need for locks or version numbers. So again, the JSON relational duality view concept solved that first object relational mapping problem. It gives you simple object persistence without the developer understanding how to map the data to relational tables, because it's like a built-in document relational mapping engine without sacrificing any of the benefits of data modularity and composability. It basically fixes the object relational mismatch. The way this is done is the application can convert their object of JSON in every language today, whether it's Python or JavaScript or Go, have easy ways to convert their objects into JSON. Once you convert the JSON, you write the JSON into the database, and it persists the data object across all the relevant tables. And this is easy for developers since JSON is extremely popular and has become the standard now for data interchange. There's a lot of benefits here. By the way, I'm only scratching the surface. There's a lot of research opportunities here as well, because with the object model known by the database, a lot of things can now be done a lot more easily than before. Things like analytics, security, etc. For instance, since the database today doesn't know anything about objects, right? They just know about rows. They really can't do anything that reflects application semantic needs. And rows really are like fragments of data. The rows are like atoms. They don't really have any, they're not complete information. They're not molecules or higher level constructs. And so what happens is the developers today implement many solutions themselves in the application tier. Now, see what you really want as a developer. When a table row changes, you don't want to know that that row changed. You want to know which students were affected by the change, which professors have a new course to teach. So now we can get notifications in terms of application objects. And then the downstream action from the notification can also be taken. Like the class time changes for a student, maybe the student now has a conflict they have to resolve because maybe they can no longer take math and science. So the idea of doing remedy, saying, oh, sorry, now your course list is inconsistent, that can be done in terms of application objects, right? So that's a big deal. Give me 1 second, I need to run to get my power adapter before I run out of charge. Sorry. I did not notice that my power is running low. This will be a perpetual problem for me. I always have this issue, sorry. Any question in the meantime while I'm looking for my adapter? Or do you want to wait till the end to ask questions?
I guess we can defer until you finish presentation.
I'll try to wrap up soon. I have a lot more slides, but I don't want to go through all. I'll go through conceptual slides. But basically, think of it this way. If you know what the objects are, the database knows that we can help with this stuff. We can help when data changes, we can replicate the object, not just the row, because maybe I'm replicating to a document database. I don't want to replicate just one row. It's pointless. I want to replicate the full object. I can also run security based on objects. So my security rules should not be table-centric. The best thing is to secure objects at the object level. Tell me, students can see their own course, their own student object, but they cannot see teacher objects. Instead of having rules at the table level. Table level rules are very difficult in the real world for application developers to handle because developers don't think of tables, they think of application objects. So all of these things are possible use cases for the database understanding object structure. I'm going to skip some of this. So one quick thing, I want to just I'll mention one more thing. Just like duality with JSON and documents, relational, you can also do duality across other data models. Another simple example is we have a concept of graph views that let you represent the graph data model on top of a relational database. So imagine a bank account graph where account rows, the vertices are accounts, and the edges are transfers between the bank, between different accounts. You can imagine this being stored in relational tables, but being exposed to the graph. Same idea that the underlying data structures are tables, but I can define property graphs on top of tables using property graph concepts that accounts are vertices and edges are essentially the transfer rows. Simple idea. And you can run very sophisticated graph queries on that structure without having to write a very complicated SQL query. Like this simple example of finding me all the money transfers between two different accounts that use up to 3 intermediate nodes. This would require 12 joins and 3 unions in SQL, but it's very simple to express in SQL because again, I expressed my intent to access the data as a graph. So this concept of duality is extremely powerful because the same application now can have a relational microservice, a document microservice, and a graph microservice on the same data. It's a very, very powerful model for abstracting data intentions. And developers can essentially get the best of these models at the same time. We are doing other things for data intention. I think intention really is fundamental to make databases work for AI, not just for app dev. We added, a concept called data usage domains, how you intend to use data of primitive data in the application and how you intend to use tables also in the application. So we have something called domains annotations, and I'll talk about that very quickly. Today, only the developer knows what data really means. Like if you look at traditional, large-scale applications, you will not know looking at the data unless you do AI on the data, which you can also do. But typically, you have to do a lot of work to infer what something is actually meant to be used for. Now, developers know that the value means a phone number or a temperature or a credit card number. But in the database, they're all stored using primitive types like varchar, number, date. And because we don't know what these things mean, we can't assist in implementing usage of the data. So if the application could, or LLMs could query the database and determine the data intention, they could do a lot better job of producing richer applications or doing app introspection. So for instance, an app might want to format a phone number or mask credit card number or enable push to call if it knows what the values are, how they're represented in the database and how they're intended to be used, sorry. Now we studied this problem. By the way, this is a pandemic project when we had nothing to do, and I was basically on weekends particularly. And I lived in Palo Alto, a city called Palo Alto then, and walked 20,000 steps every day, thinking of how we can make databases more application developer friendly. And one thing I was clear on, that the last thing any developer wants is more data types. Nobody wants that. One thing was, why don't we have a credit card type and a phone number type and a temperature type? Types are bad. Types create type conversion headaches, they destroy portability, and developers tend to ignore rich type systems. That's why JSON has only a few types. JSON is a very simple interchange format because it did not go crazy adding hundreds of types. So that's why we decided not to add types, but just to add additional information that tells you what something is meant to be used for. And we use the SQL domain concept to add what we call value. Domains are used in SQL for a different purpose. We built on that concept to extend it to represent usage. So you have your columns as always in the database. You add the domain to say what the usage is. So you can, in the contact column, you can add the information that this is of domain phone. It doesn't change the fact that the value is stored as a varchar potentially or number, but the domain is phone. So you get the application can then easily tell what the intended use case for that value is. So it's a very simple example. You could create a credit card domain that gives you a bunch of properties for that data, which are all optional, but you can declare the domain for credit cards as something based on a varchar property with different properties like constraints, display, etc. And then you can apply the domain to a new table or add it to an existing table. All of that's possible. The main thing when I add the domain, it does not require any application code changes. This is a simple addition to the database, and then you in the application or the large language model can introspect this and say, yeah, that's a credit card. I know what to do with that. Okay. The same thing with annotations, slightly different from domains. Domains are meant for values, and annotations are meant for metadata. So if I have a table of employees, for instance, I can annotate that table to indicate what the table is meant for. Think of it as like commenting for tables and metadata with slightly more structure. So it's a simple idea where I take the table definition and annotate different elements of it. And this makes it also a lot more AI friendly to work with. As in this example, I can say that the employee table, I should display the emp table should be displayed with the display name of employees. And the columns will be displayed or treated differently based on the annotation. By the way, if you look at traditional schemas, like for instance, SAP's schema, it's a very complex schema. You will not find tables there which have human understandable names because they're mostly machine generated names. And SAP has an intermediate layer that actually knows what these tables are for. And they have their own SQL language. I think it's called ABAP SQL that translates those names into the actual database schema element names. So annotations, if you can push them into the database, will allow any tool on the database to benefit from that knowledge. I'm going to skip some of this. Yeah, but yeah, AI on data requires something like this. To me, AI on data, you really need to start with a good, solid foundation where you provide as much context as possible in the source data, and then you can do a better job to do AI on the data because now you declared what data is for. You can also try to reverse engineer annotations and domains. It's never as good as the developer declaring it in advance. And in most cases, the developer knows what the data is meant. So why not just use that information? Which is why we say intention is all you need. Okay. So yeah, basically this is the vision statement that intention is essential to make databases great for app dev and for AI. It fixes the application to database mismatch. That application and databases think of data differently. That problem goes away because now the database knows the application's thoughts and requirements. It solves many of the problems that have frustrated developers for decades, like replication, security, validation, etc. rules that today in the database are table-centric, which are not what developers want. So making the database aware of actual data intention lets the database help in building the best solution. And this gets a huge benefit in overall productivity for application development. I think there's a lot of potential in this. And I've given you three examples of intent, duality views, graph views, annotations, domains, actually 4 examples. There's probably more, but if you think about the opportunities this opens up, it's huge. If you can declare the end intent of processing requirements, of modeling requirements, of usage requirements native in database through a standard framework, a standard language like data intention language, then you can do so much more for AI-based app development and app generation. So I think I would like to just leave you with that thought. I know most of you aren't database people, but I think jointly between the data scientists, the AI communities, and the database researchers, we need to really proliferate this concept of intent up and down the stack. The intent should really originally come from the developers, but in some case you can also generate them through AI. I think it's always better to have them declared by the developer because that'll be correct because the developer usually knows what they're doing. But sometimes LLMs can also do a good job in determining what something means. But intent is essential for app dev and AI to really work seamlessly with data. Okay, I think I was able to cover everything. So I'm going to stop here and then see if you have any questions.
Well, thank you very much. This is a topic very right in the time. We're talking about a lot about AI, but we don't really seriously look into the data issues and the database it deals with provides a tool for formal tools for capturing the semantics, but the LLMs at the high level, there's a big gap in between these two layers. Now I think this is a good time to take a look at this issue. Any questions? Yeah.
I mean,
Professor Yu? Professor Yu?
Oh, yes. I'm not a developer and I'm not a database man. So even though I couldn't understand details of your talk, I was much impressed by your vision. And even though I just got a glimpse of what you have talked today overall, I think I learned a lot. So first of all, I'd like to say thank you for you.
So much.
He's an economist.
So let me try to express my understanding using economics analogy of database.
Sure.
So if you consider a firm or organization, then it has an objective, and the objective is constantly changing.
Yes.
So for that objective, which is constantly changing, the firm organization had to mobilize resources and personnel and capitals and spaces. So in your case, developers have certain intent, certain objective, and then the developer have to mobilize different databases scattered over different places. obviously, excuse me, you don't want duplication of data, and you want some flexibility in you mobilizing database stored in different places, as if a firm sometimes secure resources even from abroad. Sometimes organization internalize resources by using M&As. So I think similar problems are existing in database management, and I think you have covered in a wonderful way an efficient way of managing databases for different intents, so for different objective of developers, uh, avoiding duplication and making it flexible and so on. So I want to know your view about my analogy between database management and the form organization, and whether my understanding is correct. Thank you.
I think you make an excellent point, by the way, and I think your understanding is spot on. And I think it's a very nice way to think about it, that intent is a great way to express dynamic goals and dynamic changing, requirements, because the landscape of data is very, very, rich and constantly evolving. And, companies internally make changes, companies acquire companies, companies have changes in, corporate direction. And they have a huge ensemble of database management systems from which all these decisions have to source their, information. So intention is a way to express the current, essentially, priorities, let's put it that way, the current objectives. And I've only given you examples of how intention works within one database, but the concepts that I've presented could generalize to a farm of many databases across a data mesh. And I could say that really what I want to do is surface these objects that are constructed from different sources and potentially stream them to other systems where they can take, more proactive decisions. So I think your analogy actually makes a lot of sense. I will use it if I can in the future. It's a good
Thank you.
economics analogy. I think it's a real world analogy, actually, of exactly what you said.
Thank you very much.
Any other questions from students? Please feel free to ask questions. Maybe, Tatanka, you can probably, introduce Oracle a little bit. It's not just database company nowadays, right?
Oh, yeah. Well, I can introduce Oracle. Oracle is not just, Oracle has not been just a database company for a long time, because we've always been an apps company and a database company, which is why Oracle's been around for 40 plus years. But right now, Oracle has become a cloud company, an AI company, a hardware infrastructure company, a database company, and an apps company. And we have our own application suites, but we also have a lot of vertical application areas. Like, we're very focused on healthcare. It's a big focus for Larry Ellison right now. And the nice thing about working in database organization, it's sort of the nerve center for everything. So because everything begins from the data. So you can't have a cloud without data. You can't really have AI without data, at least for enterprise use cases. And you can't have application without data. So the reason I've stayed at Oracle for so many years is because of the diversity and wealth of the the data use cases, and the fact that every few years there's something totally new comes up as a new requirement. And AI, I think, certainly has become this new big renaissance for databases, because you need data for enterprise AI. So that's the new Oracle today, which is a very different company than the Oracle that I joined back in 1995. In fact, it'll be 30 years I've been at Oracle this year. So
Wow, congratulations.
yeah, my 2-year break from Stanford became a much longer break than expected. But then that's Oracle. Oracle's it's an amazing company. I think it's one of the longest lived successful companies in Silicon Valley for that reason, because
Right.
also adapt with the times. Yeah.
Mhm. Also, it's I think one of the companies leading the Stargate project, right?
Yeah, I don't know anything about that myself, and I'm not. Yes, Oracle has deeply invested in a lot of AI infrastructure. So as a result, it is a candidate for some of the very large scale AI operations. So we have a lot of very large AI partners that are using Oracle Cloud. And literally, like I would say 80% of my day is spent on AI and related projects and related initiatives right now.
Mhm, mhm. Now I have some technical questions. This LLM is based on document unstructured. It basically trained on with unstructured document. But for enterprise applications, the precision, correctness is very important, and we cannot. In a way, LLM is kind of wrapper over, the enterprise database, for enterprise applications. So then the question is, people want to express the intention, whatever, in natural language, and then we have to translate that natural language to database queries. How we make a progress in this, arena,
We have a lot of efforts in that space, by the way. So we have a product offering called Select AI that
Mhm.
does natural language select SQL translation. Now that takes advantage of everything I mentioned to you today. So all the,
Mhm.
based on duality views, the domains, the annotations are fed into the prompt.
Mhm.
So when you tell the LLM everything you can possibly tell about the data, it can do a much better job query construction. We're also, one of the things we're looking at that duality makes possible is, you can now think of your data just the collection of JSON documents. And you can, there's many ways to now search the data in very rich, sophisticated ways, not just relational ways. So I think, the whole intent area is of central importance to AI-based app generation. So we're making deep use of it. If you look for Select AI, it's
Mhm.
available right now. It's a easy way to try this out, and it uses these techniques for natural language select SQL conversion.
Mhm.
But yeah, this is very timely for the AI era.
Right. And then regarding the MongoDB, what do you think? Why this has become popular? Now, but but MongoDB has a lot of limitations as well.
Yes.
As you mentioned, some of this. Yeah.
Well, so my, of course, I respect all competitors. So competitors are there and it's good to have competitors.
Mhm.
My thing is they became popular for the reason I mentioned, because they represent the application object natively. So for a developer, it's a much simpler thing to do a get and a put, read and write, than to do joins and updates on different tables. So the problem that MongoDB creates, developers don't see till much later. When they
Mhm.
start to find the data has lots of duplication inside of it. And they try to patch that data by adding references, which creates a different problem. So
Mhm.
it's easy to uptake, which is why it's become popular. What I found that it's difficult to live with long-term for really complex use cases. And many customers have come to Oracle saying, our MongoDB database is not scaling any longer for the
Mhm.
use cases we have because of this problem. Because now reads and writes are simple as long as you don't modify shared data. But if I'm modifying data shared by many documents, suddenly my single object right now has to become now write to 100 objects or 1,000 objects. So it's popular because it's simple, but I think it has some fundamental limits
Mhm.
because of the fact that they have not addressed the problem of data duplication. Is it popular in Korea?
I think so. Yeah, I think I guess the simplicity is in a way the key metric for the naive developers. And then sooner or later they find that it doesn't scale. And then
Right.
they're looking for then they look for alternative solutions. Yeah.
It's not that it doesn't scale because the design is bad. And the problem is
Right.
architecture is limited in what it does,
Right.
right? It's very good for simple use cases, but the minute you get to anything enterprise where lots of data is shared, and also it's very difficult to implement fine-grained security rules in MongoDB
Mhm. Mhm.
because you can only secure collections, and collections aren't enough. Maybe I don't want to let the developers,
Mhm.
the students, be able to see the professor's details,
Mhm.
but they need to be able to include the professor's name and department affiliation, but nothing else. That's very hard to do MongoDB. So security rules
Mhm.
become an application headache after that. So that's basically the issue with MongoDB, I think. But,
I mean, for the interest of student, I'll ask some questions. Actually,
Question.
and you didn't mention anything about the columnar, database here. So the analytics are still in column-wise analytics. Is also critical for
Yes.
certain enterprise applications.
Of course, columnar is still there. So I mean, columnar is like a lower level storage organization. So
Mhm.
in the duality view, you can easily have a table that's columnar, no problem. A table that you want to run analytics on. Maybe you want to analyze sales, for instance, and you want the sales table to be columnar. But you can define duality views where every sale includes the sale fact row plus all the dimension rows. So you can see the entire data in one read. So they're two complementary mechanisms. Columnar gets you very fast analytics, and duality gets you the right input-output format without doing a lot of relational to document transformation.
Mhm.
I see columnar as sort of an orthogonal benefit to analytic applications, but works. Duality views will work with columnar
Yeah.
data, which is just fine.
I guess Oracle can do that, but MongoDB cannot do.
MongoDB cannot do that. They don't have the ability to do that. So that's a good point.
Right. Right. So
Actually, analytics on document database are very, very weak. You really do. I mean, the type of analytics that you and I have done in our products that we worked with on HANA and Oracle database, MongoDB can't even come close to expressing those kind of analytics. It simply does not have the infrastructure in documents. You can't do it with documents alone. You need a relational engine really to do that. So
the final question, this is more, I just saw the news that the Anthropic and the Databricks made a deal that they sell each other.
yeah,
Just like in the old days, SAP and Oracle,
yeah. Yeah, that's something. Yes, we're watching the space. There's stuff happening, and there's a bunch of things that are in the works right now. So I'm not allowed to speak about any of them, but yes, certainly tracking. One thing is the thing that I like about Oracle strategy is we try to, and one of the analysts I spoke recently said this to me, that we try to be AI secularists, that we will not legislate your choice of AI. Our strategy is to do the best with AI of your choice, because Anthropic works well some use cases. So in some cases, something else works better. So for us, rather than try to say, hey, we're going to, essentially pick one, we feel like the best strategy for database is to work in the best way possible with any AI platform. And that way the customer can choose that based on their, business requirements. But this area is moving fast, and I think there'll be consolidation in the future. There'll be a lot of interesting business activity. But from a technology standpoint, our job is everything we're doing in the database for AI. We're trying to make it support any AI framework of the customer's choice. So
I guess you have at least one close friend, OpenAI, as part of a Stargate project.
yeah, well, we have, like I said, we have there's lots of things going on in that area. Actually, I'm happy not to be like in that area, because that area is in very high rate of churn. In the database group, we have the luxury of actually picking the best solutions that are the most general purpose, which is what I like, we like to do. So whether it's Stargate or a different gate in the future, we have the best data technology possible for handling the requirements that come out of that. One thing I've learned over the years is anytime you special case solutions to fit a particular stack, it's usually fails because that stack eventually gets replaced by something else in the future. Like, if you remember in the old days, we had something called Corba that everybody used. It's dead and gone and buried right now. So anybody who built Corba-centric databases, basically, they were wasting their time. But to be generic, I think it's important to look at the requirements as an evolving set and build the most general landscape possible to handle all the needs that customers might have.
Okay. Well, thank you very much. Thank you for sharing your vision and thought, and also answering questions.
Sure.
And I
Thank you.
look forward to seeing you in
I would
Palo
love to
Alto.
I would love to see you in Palo Alto and in Seoul as well. I prefer Seoul to
Oh,
Palo
well.
Alto. If I can choose, I would prefer Seoul, but Palo Alto would be good as well.
Okay, come to Seoul anytime.
Okay. Bye-bye. Thank you so much.
Okay, thank you.
Thank
Yeah,
you.
bye-bye. Mhm.